In this video, we're going to take a look at Chapter 1, Section 2 from our textbook. In the first section, we looked at angles. And so in this second section, we're going to move on to look at what we can do with angles. So in 1.2, we have angle relationships and similar triangles. Similar triangles is the big, most important one here. But we're going to begin with some geometric properties and then look at triangles and then, more importantly, similar triangles. So let's take a look at the angles that are formed when two lines cross. When they have these angles here, you can see that there's purple angles drawn in here with purple arcs and then these little orange colored arcs. So I'm going to label these 1, 2, 3, and 4, these 4 angles that are made. These are called vertical angles. Well, specifically, you have vertical angles for the opposite pairs here. So 1 and 3 are vertical angles, and 2 and 4 are vertical angles. And so when these two lines cross like this, the opposite angles formed, the vertical angles, are equal to each other. So 2 and 4 are equal, and 1 and 3 are equal. And this is going to happen often, that two lines cross and that you have this occurring. Okay, so here's a good example of that. Let's say we have these two orange lines that are parallel. And you may recall that from algebra. Two lines are parallel if they sort of both go in the same direction and they never cross each other. And then you have this additional third line, this purple line in our diagram here, that crosses the two parallel lines. So when that happens, we're going to call that a transversal. And you can see that in each case, the transversal, when it hits one of the parallel lines, forms some vertical angles. There's this upper set here, and then there's this lower set of, in each case, 4 vertical angles. And as we learned on the previous example, the vertical angles are equal to each other. So you could see 1 and 4 are equal to each other, 2 and 3 are equal to each other, 5 and 8 are equal, 7 and 6 are equal, because in each case those are vertical angles. But also the transversal crosses the parallels at the exact same angle. Angle 8 and angle 4 here are the same angle because the parallel lines go in the same direction and the transversal crosses them both at the same angle. So that means 8 and 4 are the same, but 4 was a vertical angle with 1, so those are the same, and 8 is a vertical angle with 5, so those are the same. So these pair are the same, these pair are the same because of vertical angles, and we just said 8 and 4 anyway. So there's a bunch of angles that end up being equivalent and has relationships. So there's going to be some tables now to summarize these relationships. All right, so first of all, of those angles numbered 1 through 8, if we look at angles 4 and 5, those are called alternate interior angles. They're on the interior because they're both on the inside of these parallel lines that we got above. And we can figure out that they end up being the same because 4 sort of matches up with the first angle that we drew up in the upper left corner up here. Those are the same, and then that matches with the number 5 because they're forming the same angle with the parallel lines. So those angles are equal, and then similar, 1 matches with 4, which matches with 5, which matches with 8, so 1 matches with 8. And as we see on the lower part, those are alternate exterior angles versus the interior from above, because they're on the outside of the parallel lines. And they also have the 3 and 6 here, and also 2 and 7. So here's 2, and here is 7 down here, that those are also equivalent. Now you kind of could have figured this out from the picture and just working out with the vertical angles, but they're going to specify them like their own little properties here when you have this situation. So we have alternate interior angles, and alternate exterior angles are equivalent to each other. So now we're going to look at angles 4 and 6 out of those initial 8. And the statement here is those are referred to as interior angles on the same side of the transversal. So we can kind of see that's where they're located. And that these angle measures add up to 180. And we may recall that adding up to 180 is called supplementary. So we can kind of see that because any two angles formed to a line would add up to 180. And as we see in the lower box here, 6 and 2 are corresponding angles, so that those are equal to each other. And if we see 2 on the upper box here, then 2 and 4 would be supplementary and add up to 180. And since 6 is the same as 2, then we can conclude that 4 and 6 add up to 180, sort of with a little substitution there. And anyway, so these two angles on the inside of the parallel lines on the same side of the transversal end up being supplementary or add up to 180 degrees. And we could get corresponding ones on the other side. So 2 is the same as 3, 4 is the same as 6, which is the same as, 4 is the same as 8, which is opposite to 5. So we could also get 3 and 5 are supplementary, and of course, as I was just using, 2 and 6 are corresponding angles, which we can see are equal to each other. And so their example to illustrate these properties is kind of like the other ones we've looked at, in which they give you a transverse across a couple parallels, and they label some of the angles. And it says we're supposed to find the measures of angles 1, 2, 3, and 4. And of course, they, for a couple of the angles, give an expression for the measurement of that angle using degrees and using the variable x involved. In this case, we can start with 1 and 4, which are the ones that they've given the expressions for. And we can see those are what were labeled as alternative exterior angles up here somewhere. But as it states here, these were alternate exterior angles, which means that they're equal. And you could kind of trace that through without having to even know what the names were. 1 is the same as 3, 3 is the same as 4, so 1 is the same as 4. But if they're equal, then we can create this equation here by saying, well, here's angle 4's expression, here's angles 1 expression, and since they have to be equal to each other, then we can put them on both sides of an equation. So they have the equation here, but we can recognize that from what they said above, gets us that these are equal. And then we can create the equation where 3x plus 2 is equal to 5x minus 4, because we know that these two are equal. And so number 1, they wrote on the left, number 4, they wrote on the right, and then they solve, and they get the value for x. Now remember, x is not one of the angles here. We plug x over into these expressions, and they're showing here on the bottom of the slide that they plugged it into expression for number 1. And if you do 3 times 21 plus 2, since x was 21, you plug that in for x. If you do this calculation, you get 65 degrees. And so then we know that angle 1 is 65 degrees. Well, we also know that angle 4 is 65 degrees because we know that they were equal. And that also means that angle 3 is 65 degrees. And so the only one we have to then think about a little bit is maybe angle 2 over here. But we can sort of quickly get several of these angles that way. If we look on the next slide, they plugged the x value into number 4. They also got that, and then they say angle 2 is the supplement of a 65 degree angle, and so we can get its measure, which they haven't listed here, but the supplement would means it adds up to 180, so that would give you like 115 degrees. And then we know angle 3 is equal to 65 degrees as well. Okay, so yeah, this is a typical type of example to illustrate the theorems from above. But we really want to get to the heart of the matter, which is similar triangles. We begin moving in that direction by just considering the angle sum of the 3 angles in any triangle. So anytime you have a triangle, 3 sides, 3 corners, 3 angles, the sum of the measures of those 3 angles is 180 degrees. Any triangle. Doesn't matter shape or whatever. If you have 3 sides, those 3 angles are going to add up to 180 degrees. So that's a very nice, simple rule that's very, very helpful as we begin to look at angles inside of triangles. So we can use that immediately with an example problem using this fact, in that if we have any 2 angles in a triangle that we know, since the sum has to be 180, we can figure out the third one. So in this problem, the measure of 2 angles of a triangle are 48 degrees and 61 degrees. Find the measure of the third angle, x. So we can write an equation that the 2 angles we know plus the one that we don't know, the 48, the 61, and the x, they add up to 180. And then you can solve for x by adding up the angles you know, subtract from both sides, and in this case we'd see the last remaining one is 71 degrees. So this is a nice, simple idea and easy to apply, but the end result is anytime you know 2 angles in a triangle, you can figure out the third one. Okay, so now let's look at different types of triangles. And when we're thinking about different types of triangles in terms of an angle, the angles inside, we begin where all 3 angles are acute. So if all 3 angles in the triangle are acute, and again that means less than 90 degrees, then we call that an acute triangle. So then the next possibility is that one of the angles is not less than 90 degrees, it's actually equal to 90 degrees. And if one of them is equal to 90 degrees, you may recall from algebra, if there's one right angle in there, this is a right triangle. Now, as soon as one angle is equal to 90 degrees, and they're not all less than 90 degrees, then the other 2 angles add up to the other 90 degrees, because all 3 add up to 180. So if 90 degrees is taken up by one angle, then the other 2 angles have to add up to the other 90 degrees. And that tells us something. If we have 90 degrees here, and the other 2 add up to the other 90 degrees, then that means that those other 2 angles are complementary. That's the word we used for when 2 angles add up to 90 degrees. And so if you have a right triangle, then the 2 angles that are not the 90-degree angles, those 2 angles are complementary, and they add up to 90 degrees. So maybe 40 degrees and 50 degrees, or 30 degrees and 60 degrees. If one corner is 90 degrees, the other 2 add up to the other 90. So we'll just label these as complementary. All right, so then if we move on to our last triangle, if I have that one angle go to be larger than 90 degrees, then it's called an obtuse angle, and we have an obtuse angle triangle is called an obtuse triangle. And that's where this one angle is larger than 90, but of course only one angle can be equal to or larger than 90, since the other 2 then have to add up to the rest to get to 180. And you can imagine then that if you do have a big angle that's even more than 90 degrees, the other two angles are starting to get pretty small. And so when you have one of these sort of extra wide triangles with one obtuse angle in them, then whatever's left over for the other 2 angles will not be very much. And the closer the angle that is larger than 90 degrees gets to being 180 degrees, then you can have sort of very skinny triangles where the other 2 angles are very slight. Maybe try to draw one sort of here. Yeah, so if you have like a really big angle here, the other 2 angles are very, very small in these little single skinny triangles. And this is an example of a more extreme obtuse triangle. Okay, so after we consider these angles, we move on to considering different kinds of triangles based on looking at their sides and the lengths of their sides. So the simplest starting point would be if all 3 sides were exactly the same length, all equal. then we would call this, as we have in this left example, an equilateral triangle. All sides are equal. And we indicate that on the triangle by drawing these little hash marks through each side. And so if you put one hash mark on one side and a hash mark on another side, those are the same length sides. And so if all three have a single hash mark, all three are the same length. So the next possibility, as we see in this picture, you have single hash marks on two of the sides that match, but then the third side has two hash marks. So that means two sides are equal, the ones that have a single hash mark each, and then the third side is some other length. That's called an isosceles triangle. And so we can see by the hash marks, these two are the same, so those two sides have the same length. And then in this case, the one on the bottom with the double hash marks, that length is different than the other two sides. And then, of course, finally, as with many triangles, none of the sides are equal. No sides have the same length. So you give one hash mark, two hash marks, three hash marks when no sides are equal. And then we call that a scalene triangle, just the name of that type. Now, this just helps us talk about and refer to the shape of triangles and properties of the triangles, depending on if there's a possibility that some of the three sides are actually equal in length, either all three sides, two sides, or all three sides are different, as in a scalene triangle. So we've looked at angles in triangles, like right triangle, obtuse triangle, acute triangle. We've looked at equilateral, isosceles, and scalene triangles to help us just discuss and summarize different triangles by their shapes and their side lengths. And now we can move on to the more important concept. Now we can talk about similar triangles. So we begin by looking at what it means for two triangles to be similar triangles, the key similar triangles here. For triangle ABC to be similar to triangle DEF, the following conditions must hold. And actually, this slide is not exactly correct, so I'm going to try to tell you it in the best way I can. For two triangles to be similar, only this first condition must hold. It says both conditions, but only this first one needs to hold. Corresponding angles must have the same measure. That's the only one you actually need, and then you have similar triangles. So they have the second one down here, but anytime the first one is true, anytime the three angles of one triangle are the same as the three angles for the other triangle, then this second condition you get for free. Meaning that will also mean that corresponding sides must be proportional. And I need to explain what that is, but this property is like a free property, meaning you get this when the first thing is true. So what does it really mean to be similar triangles? How can we think of similar triangles? So what is it if two triangles have the same angle measurements? Well, imagine that they have the exact same shape. So if I go up here, we have these different shapes. Look at this triangle on the right, the scalene triangle. If I have another triangle that has all three angles that are exactly the same as this one, then the only way it would be different is if it was bigger, like if I zoom in like this, or smaller. That way I'll have the exact same shape, but just a different size. And so when you have two triangles that have the same three angles in them, then it'll just look like one is a bigger version than the other of the exact same triangle, like you zoomed in or zoomed out to get a bigger or smaller triangle. So that's what similar triangles are. They're the same, it's like the two different sizes of the exact same triangle. So I'm going to try to draw and extend each of these sides here to be twice as long as they were. So this left side here, I've drawn it up about twice as long. And I'll try to draw down and out to the side here. So then the bottom will be twice as long as the bottom was before. And then the angular side up on the upper right will be twice as long as it was on the small version of the triangle. So this doesn't look that great, but hopefully you get the idea. So if I do that, then the new triangle I've created, all the lengths are twice as long as the original triangle I started with. But we can also see that the angles are all the same. So it's kind of like a zoomed in version of the original triangle that now just is twice as big as it used to be when you look at it. But notice these two angles are exactly the same. So angle 1 is the same in the little one and in the big one. Angle 2 is the same in the little triangle and in the larger version. And angle 3 is the same because it's the exact same corner in both of them. So then this way we do have similar triangles, but the larger one now has all of its sides twice as long as the original one that I started with. And so this is what they're talking about in part 2 here, that corresponding sides must be proportional. That's what you get for free when you have two similar triangles. That the corresponding sides might be side 1 of the small one corresponding to the same side 1 of the bigger one. And in this case, proportional means that basically they're a constant multiple. Let me try another little example with two side by side. Let's say I have a triangle with lengths 1, 2, and 3 on the sides, and I draw one that's the same shape but twice as big. So all the angles are the same, but now the side that was 1 has grown up larger to be of length 2. And the side that was 2 has now doubled in length and is size 4, and the 3 on the bottom has now grown to a length of 6. So these are similar triangles, with the bigger one being twice as big as the smaller one. So what that means is that as I doubled or multiplied by 2 all the side lengths, then the ratios are like fractions of their corresponding sides will all end up being 2. So for example, if I make a fraction of the larger side, let's change colors here. The larger size, it went from 1 to 2. So if I'm making a fraction of those, a ratio, that would be 2 over 1 if I'm making the big side in a fraction divided by the small side. That's a ratio. A ratio is a fraction. So if I take the large side and divide by the small side, that would give me a ratio of 2 divided by 1. And if I do that with the other side, I would get a ratio of 4 divided by its original side length of 2. Those are corresponding sides, the 4 and the 2. And similarly, 6 on the bottom would divide by 3. And the thing to see is that in every one of these ratios, the multiple that I get is 2. They all reduce to 2. They're all equal. The corresponding ratios must be equal. In this case, they're all equal to 2, because that's how much bigger the larger triangle was compared to the small one. And in this way, you can kind of see what the multiple is. Now, it may not come out nice. It may not be an even number like twice as big. Maybe the larger triangle is, 5/7 or 7/5 the size. In any event, so let's look at this first example. So when you have similar triangles, we know that all the corresponding angles are the same. So in this particular first example, we see in the small triangle, the three angles are 45 degrees, 31 degrees, and 140 degrees. So we are asked to find angles B and C. We see the 45 matches with the 45. And so then each of the angles B and C will match with the same corresponding angles in the original triangle. So if I match up angle C on the bottom left in the big one, that matches with angle P in the small one, which was 104 degrees. So that means C measures 104 degrees because C corresponds to P. Similarly, B corresponds to M. M is 31 degrees, so B measures 31 degrees. So when you have similar triangles, the corresponding angles are exactly the same. Now it's that second part, that free property that we get, is where things get interesting. So with these two triangles, you can see there's a bigger one and a smaller one. And again, because this is a nice example, we can see by observation that the one side that's known on the small one, which is E to D, which is of length 8, that corresponds with the C to A size on the bigger one. So 8 turned into a 16 when we blew up the size of the triangle. And so again, the big one is twice as big as the small one. And so if I make that observation that the big one is twice as big as the small one, then all the big sides will be twice as big as their corresponding sides. And if it wasn't a nice number, you can still get it by making this ratio, but in the ratio, still big to small comes out to be a nice even 2. So if the big one's twice as big, well then, for example, on the bottom, you had 24 when the larger side was there, so the small one must be half of that, which is 12. And similarly, the big 32 length side, on the smaller one, it must have been half of that, which would make the smaller one 16. Now, that's because this is a nice, easy ratio. One's twice as big as the other. So let's look at the process you would use. You can set up a proportion. A proportion is where two fractions are equal. And so basically, all corresponding sides proportions will come out with equal fractions. And so they do that here. This is what a proportion looks like, a fraction equal to a fraction. And so basically, you'll say something like, side 8 corresponds to side 16 in an equal way that side DF on the bottom of the little triangle corresponds to 24 on the bottom of the big triangle. The little to the big has to match up with all of the corresponding sides, so we get this proportion. When you have a proportion like this, you may or may not recall from earlier classes that you can solve a proportion and then you can solve for the missing side. So in this case, the missing side was DF, and we compared that to 24, and we compared 8 to 16, and then we set up this proportion, and we solve with a process called cross-multiplying. When you have a fraction equal to another fraction, the diagonal products have to come out equal. So you can convert the equation with fractions in it into an equation of just the diagonal products when you do this thing called cross-multiplying. So if I cross-multiply this way, I get 16 times the DF side, which I supposedly don't know when I'm using this method. And that's equal to the other direction, which is 8 times 24. And now you can solve that equation for DF. I would divide both sides by 16 to solve for the unknown DF. And then if I do the arithmetic on the right, I get the answer. And if I do 8 times 24 divided by 16, I get 12. And so that confirms with what we could see in this simple example, because the big one was just twice as big as the small one. But this gives us a procedure that we can use. And that way, if it doesn't come out nice, we have this procedure kit to get an exact value, even if it's not so obvious and friendly, like one being twice as big as the other, for example. Now, I think they walk us through the solving process. If you see here, they took that proportion, and they took the diagonal of 8 times 24 by going from upper left to lower right, and then they said that's going to be equal to the other diagonal of 16 times DF, which is basically the same thing I did, but reverse order. And then they solved, and they got the 12 for the DF, just like I did above here. Okay, so this is, and then you could do the same thing for the EF side by setting up another proportion, which they do right after that, and I'll let their example follow through with how they got the EF side, which we were able to see easily as 16, and then they get the same thing by setting up another proportion. Let's see. So here's the one that we just did, and then they can see also they set up a proportion for EF, where 8 is to 16, the same way that EF would be to 32, and they got EF was 16. Okay, so let's finish with this final example here, which is similar triangles in a sort of described real-world situation. It says, workers must measure the height of a building, flagpole. So here's the building flagpole, so I'm going to put a little question mark here because we don't know what that is. They find that at the instant when the shadow over 18 here from the building is 18 meters, at that same point in time, the shadow from the flagpole that we don't know the height of is 27 meters. And so as we can see, these are the bottoms of these two triangles. 18 is the shadow of the building, and 27 is the shadow of the flagpole. Now, because the flagpole is straight up and down and the side of the building is straight up and down, we have these right angles in the corners. And similarly, the sun is shining on the building and the flagpole at the exact same angle of the sun rays, which is sort of up here. The angle of the sun ray coming off the building is going to be the same as the angle of the sun ray coming off of the flagpole. And if these two angles are the same in these triangles, since they both have to add up to 180, then that last angle in the corner down there will also be the same. And therefore, these are similar triangles. And therefore, the bigger one is just a scalar multiple of the bottom one, or a scaled up multiple of the bottom one. But unfortunately, in this case, 27 is not a nice even multiple of 18. So we have to kind of say, well, what did you multiply by 18 to make it become a 27? It's not twice as big. We do see that they're similar, so there has to be a multiple. So we can do the proportion method, but let me just try to keep the big picture in mind here for a second. How did 18 change to become 27? What is the increase? Because the smaller one did get bigger. What is the increase from 18 to get to 27? Well, we can see that it's 9 more. Like if I take the difference between the two, I can see that if I have an 18, I could add 9 to it to get to 27. So that's what the increase is. But of course, we need a multiplier to get big. We can't just add 9 to all the small sides to get the big sides. That's not becoming twice as big or 3 times as big. So when we make this jump and we add 9, what we can observe is that 9 is half of 18. And so that increase of 9, increasing by half, that's a 50% gain. And that you can think of as a percentage gain is a multiple. So basically, we gained 50% as a multiplier, got 50% bigger when going from 18 to 27. That means all the sides will get 50% bigger. That means the height of the building, which is at 10, when I go to the similar triangle with the flagpole, will grow to 50% more than 10 or 15. You add half of 10 to 10. To get 5 to 10 would give you to 15. So we can see, if we sort of feel comfortable with this percentage of growth, that the flagpole height is 15 meters here. However, I'm not expecting students to do problems like this way, and we do want to practice our proportions using similar triangles and proportional sides. So instead, we can make our ratios of corresponding sides and set them equal to each other, where the unknown flagpole is one of the heights involved. So if I set up a proportion here, let's see, we're going to do, I guess the sides we know are the 18 and the 27. So I can say 18 is to 27 as a ratio equal to, or the same way that the height of the building, 10, would be to the height of the flagpole, which is unknown. So I put my question mark there. And so with this proportion, I can solve for the unknown value. We can cross multiply and solve for the variable. All right, well, let me write this as a variable. Instead of a question mark, let's say we call that an x. So if this is an x, then we have a little equation we can solve for x, and I would cross multiply 27 times 10 would be equal to 18 times x. And I'm kind of out of space on my slide. If I move up here a little bit, then x would be equal to 10 times 27 divided by 18. And I can multiply and then divide, but I can also simplify this by factoring. 18 I can factor into 9 times 2. 27 is 9 times 3, so then the 9's cancel. 2 goes into 10 5 times. So after all that, I'm left with 5 times 3, which is 15. And we knew that was going to be the answer just because I knew it was 50% bigger. But you could see how we solved it with a proportion there, and we got the same answer that I did sort of the other way. So what did they do here? Oh, they didn't do it at all. They just confirmed that the answer is 15 meters high. Okay. So yeah, so this is what the solution looks like if we write it out in detail, and and we used a proportion to solve the missing side of a similar triangle. And so this is where our slideshow ends, and that was the most important big concept. So you want to do a lot of examples of similar triangle problems and solving for missing sides. We're going to be doing that consistently through the class. And hopefully this will give you an idea for how to do that, and you can warm up to the skill and the concept.